All right, welcome back, calculus students. This video is on the substitution rule, sometimes referred to as u-substitution for integration. So it states as follows. If u equals g of x is differentiable and its range belongs to an interval I and f is continuous on that interval, then the integral of f of g of x times g prime of x dx is equal to f of u du. So the idea is as follows. We have some messy looking integral and it involves a composition of functions and also the product of the derivative of that inner function. We want to clean it up and make it this nice integral, easier to anti-differentiate. So how do we begin? We have to first make a good choice and figure out what u is. U is g of x, remember. And we'll talk about how to select u appropriately. That can be the trickiest part. And then from there, we have to change our integral completely from being in terms of x to being in terms of u. So that means I have to figure out how to express dx now in terms of u. And the way you do that is you take the derivative once you know what u is equal to. So that means du dx would equal g prime of x. And so du is equal to g prime of x dx. And you can see that substitution happening here, right? So g prime of x dx gets replaced with du, and then f of g of x becomes f of u. And then we anti-differentiate this easier, less intimidating integral over here, and then go back and substitute so that our final answer is in terms of x. All right? So here we go. Let's get started. Evaluate the following. So example 1, we have the integral of x squared times x cubed plus 5 to the 9th power dx. Now it would be a nightmare to expand this, right? To take x cubed plus 5, raise it to the 9th, and then multiply by x squared just to anti-differentiate term by term. Way too painful. Do you see a function being composed with another function, and can you identify what g of x or u would be? Well, it looks like I have some function being raised to the 9th power, so I suspect that I should let u equal x cubed plus 5. How do you know if that's a good choice? Well, the derivative of u, du, should be sitting somewhere in that integral. And if I take the derivative here, du dx, I would get 3x squared. Now that's not exactly what I have. I have x squared, but that's no big deal. I can fix it by a constant. So let's see. I want to make this match exactly with what I have in my integral. So I have an x squared and a dx here. So du is equal to 3x squared dx, which means 1/3 du is equal to x squared dx. So I can substitute 1/3 du for this little kidney bean here for the x squared dx. So now let's rewrite our integral entirely in terms of u now. So we have the integral, instead of x cubed plus 5 to the 9th, now that's u to the 9th. And then instead of x squared dx, I have 1/3 du. Okay? Now to evaluate this antiderivative, let's take the 1/3 outside. Then I have u to the 9th du. And this is easy to anti-differentiate. I'm just going to increase the exponent by 1, divide by the new exponent. So I have 1/3 times 1/10 u to the 10th. Don't forget your plus c. And then for your final answer, you have to express everything in terms of x, right? U was just a tool, that substitution, to help us evaluate the antiderivative. But nobody wants the final answer in terms of u. So we have 1/30. U was x cubed plus 5 raised to the 10th plus c. Okay. And if you'll notice, you could take the derivative of this and make sure that you get back the original function. And when you take the derivative, you would bring that exponent down in the front, the 10. So you would have 1/3 because you'd have 10/30, and then you would have to apply the chain rule and multiply by 3x squared. So u substitution is used when you need to integrate and undo the chain rule. When you have a derivative in which the chain rule was applied, you need to use u substitution to integrate. Okay, let's look at another example. And it's totally normal at first to make the wrong choice for u. It just takes a little bit of expertise and experience, and then you'll make the right choice. Okay, so here I have e to the x times sine of e to the x dx. Okay, now do you see a composition of functions? You want to let u be the inner function in that composition. Well, I see I have sine of e to the x, right? Instead of just sine of x. And then if I were to let u equal e to the x, is that a good choice? Well, do you see its derivative sitting somewhere in this integral? Well, yeah, du dx is e to the x, which means du is equal to e to the x dx. And I see that exactly right here. Okay, I really recommend drawing that little kidney bean shape. It's going to help you out. So now let's rewrite our integral entirely in terms of u. So now I'm going to have sine of u, not e to the x, and then e to the x dx gets replaced with du. Now make sure you change your integral from being in terms of x to being entirely in terms of u within one step. Don't have x's and u's mixed within your integral, because that's not well defined, that's incorrect and improper, okay? And then let's see here. Do we know the antiderivative of sine u? Yes, it's going to be negative cosine of u, and then I need a plus c. And then don't forget to go back to the original variable, which was x. So I have negative cosine of e to the x plus c. All right, looks good. All right, let's move on here to the third example. So I have the integral of dt over cosine squared t times the square root of 1 plus tangent t. Now maybe at first glance it's not clear what to do. Do you see any sort of composition? I mean, I see this function underneath the radical. So I feel like maybe u should be 1 plus tan t. Right? And just as a heads up, if you ever have like a constant added to another function, you always want to include it when you're deciding what to let u equal. You don't want to have u just be tan t, because when you find du, right, du, the 1's going to go to 0. So you're just going to have secant squared t dt. Well, do I see a secant squared t somewhere in my integral? I do. That's what cosine squared is in the denominator. So I can actually first, let's rewrite this so I'm all set up to switch to u's smoothly. I can rewrite this as secant squared t dt over the square root of 1 plus tangent of t. Okay, so it looks good. So du is going to replace secant squared dt, and then u is 1 plus tan t. So that's going to be my u. So now I'm going to switch all in one step to writing my integral in terms of u. So I'm going to have 1 over rad u du. Okay, and then now let's anti-differentiate. So this is the integral u to the negative 1/2 du. I'm going to add 1 to the exponent, so it's going to be u to the positive 1/2. Divide by 1/2, so I'm multiplying by 2, so I have 2u to the 1/2 plus c. And then let's rewrite everything in terms of the original variable. So I have 2, let's switch to radicals, why not? Rad 1 plus tangent of t plus c. All right, how are we doing? Example 4. The integral of tan inverse of x over 1 plus x squared dx. Okay, any ideas? I don't see a composition of functions, but do you see something that you could let u equal? And then do you see its derivative also sitting somewhere? Well, look, if I let u equal tan inverse of x, then du over dx, I'm just moving the dx already over, okay, is going to be 1 over 1 plus x squared dx. And that's exactly what I have right here, okay? So then in one slick maneuver, I can rewrite this now as the integral of just u du. Okay, so this is going to give me 1/2 u squared plus c, which is going to be 1/2. Now this might look a little weird, so you have tan inverse of x squared plus c. All right. Now, if you didn't learn your derivatives well, especially for those inverse trig functions, then maybe you wouldn't have even thought to do that, which means go back and make sure you memorize them. Otherwise, you're going to really struggle with this section. Okay, example 5, integral of tangent theta d theta. This one's going to come up so much for the rest of your math career, you might as well memorize it, but it's such a slick way of deriving it, so we're going to do it together right now. So for tangent theta d theta, you're going to rewrite tangent as sine theta over cosine theta d theta. Okay, now you might get confused because you could say, well, should I let u be sine theta because du is cosine theta? But remember, du is never in the denominator. It needs to be multiplied by the function. It needs to be in the numerator, basically. So you actually want to let u be cosine theta, and then du would be negative sine theta d theta. Okay, do you see that? Don't worry about the negative. We can deal with that. So negative du is sine theta cosine theta. Negative du is sine theta d theta, excuse me. Okay, so d theta cannot be, du cannot be in the denominator. All right, so now let's rewrite our integral in terms of u. So I'm going to have the integral 1 over u du, and let's put the negative out here. All right, well, what's the antiderivative of 1 over u? It's natural log absolute value of u, right? So I have negative natural log absolute value of u plus c. And this gives us negative natural log. I'm going to replace u with cosine theta plus c. Now, technically, this isn't wrong, but you can do something so slick with logarithms. Remember, that coefficient I can rewrite as an exponent on the argument. So I can write this as natural log of cosine theta, absolute value, to the negative first plus c. And cosine theta to the negative first, that's 1 over cosine theta, which is our good friend secant theta plus c. And so this is how you're going to see the antiderivative of tan theta d theta written most of the time, because 1, there's no negative in front, so it's more visually pleasing. And 2, tangent and secant have had such a nice relationship over the years, right? We have a good Pythagorean identity together back from trig days. Derivative of tangent is secant squared, so it seems natural that if you have the antiderivative of tangent theta, you want to express it in terms of secant instead of this negative cosine. Okay? From here on out, you can memorize it unless you're asked specifically to find the antiderivative of tangent theta d theta, then I would show some work. Okay. Example 6, we have the integral of x over 1 plus x to the 4th dx. All right, so maybe you're thinking to yourself, ooh, let me let u be 1 plus x to the 4th. And then you'll quickly see things not working out. So du would be 4x cubed dx. Do you have an x cubed dx? No, you have an x dx. So that was not a good choice for you. Oh no. So let's leave this bad choice so we don't do it again. And also it's helpful when you look back over your work. Instead, let's think here. I want du, right? I want du to end up to be x to the first power, right? Which means u needs to be 1 degree higher. So u would need to be x squared. Let's see if that works out for us. I'm hopeful. So let's let u equal x squared. Then du would be 2x dx. Okay, I only have x dx, so that means 1/2 du is x dx. All right, I can switch everything to be in terms of u now, because remember, x to the 4th, that's x squared squared. So I could write that as u squared. So my antiderivative becomes 1/2, just bring that 1/2 out there, integral du over 1 plus, x squared squared, so u squared. Do you know this one? Do you want me to write the du off to the side? Does that help? 1 over 1 plus u squared du. You don't have to do this stuff unless it helps jog your memory. This is our good friend tan inverse. So this is 1/2 tan inverse of u plus c. And then remember, you got to go back and replace u with x squared, right? U was equal to x squared. Let's put some parentheses so it looks nice and neat. Okay, looks good. Now, example 7 is a little bit of a different style of u substitution. So before we do that problem, I want to do a little warm-up problem, actually. Okay, this is like additional warm-up. Say you have the antiderivative of x times the square root of x plus 1 dx. Okay? Now look here. In the past, you weren't given a problem like this to integrate, because if you had a radical, you usually would rewrite it to the 1/2 power, and then you could distribute it or anti-differentiate it in some way. And we're stuck here because if I were to distribute this x underneath the radical, it would just make life so much worse, because then we would have an x squared underneath there distributed to x plus 1. So I'd have this messy expression underneath the radical that I still couldn't anti-differentiate. So that does us no good. So you're probably looking at this and going, oh man, I wish they were switched, right? I wish this was x plus 1 and this was just x. Wouldn't that be so nice? Well, in math, you don't just sit around feeling sorry for yourself. You're going to make it happen. So what we're going to do is use u sub. I'm going to let u be x plus 1. Never just let u equal x. That's pointless. You're just changing your variables around, okay? Now, du is dx. Okay, that's good. So this part's taken care of. That's going to be rad u. This is going to be du. But what about this x I'm stuck with? Well, look, you got to do something kind of slick. Since u is equal to x plus 1, that means x is equal to u minus 1, right? So now I can rewrite my integral entirely in terms of u's. So I'm going to replace the x with u minus 1. Rad x plus 1 is going to be rad u, and dx is du. Now look and compare. I want you to see what beautiful thing just happened here. What's underneath the radical? Well, I switched it from x plus 1, now it's just u. And then what's not underneath the radical? Well, it was x, and now it's u minus 1. But I'm so happy because I can rewrite this now. This is integral u minus 1 times u to the 1/2 du, and now I can distribute this inside, right? Since there's no radical around u minus 1. Okay, so I have u times u to the 1/2, so that's going to be u to the 3/2 minus u to the 1/2 du. And then we can just anti-differentiate term by term. So I'm going to have u to the 5/2 with 2/5 in front minus, and then this is going to be u to the 3/2 with 2/3 in front plus a c, and then go back to the original variable. So u was equal to x plus 1. So I have 2/5 times x plus 1 to the 5/2 minus 2/3 times x plus 1 to the 3/2 plus c. And then we are good to go. Ooh, come back. Okay, so I wanted to show you this example because sometimes you're going to let u equal something, and then within that statement, you're going to have to rearrange and solve for the original variable so you can make a complete transformation of variables within your integral. All right, now let's go back to example 7, and we're going to do something kind of similar, but example 7's one level more intense. So we have 7, integral of x squared over rad 1 minus x dx. Okay, so you might try a few things, letting u equal 1 minus x. But the cleanest way to do this problem is just to let u equal rad 1 minus x. Okay, And then from here, you're going to have u squared is equal to 1 minus x, right? If I square both sides, which means x is equal to 1 minus u squared. Okay, where are we going with this? Well, dx is going to be equal to negative 2u du. And now I'm ready to make my change of variables. You may not believe me, but here we know dx is equal to negative 2u du, right? X squared, well, I can just replace it with 1 minus u squared squared. And then what about this 1 minus x underneath the radical? Well, that's what u is. So everything's accounted for. Now I can change my entire integral to be in terms of u. So let's rewrite it accordingly. So now I have the integral. X squared is going to be 1 minus u squared squared over, instead of rad 1 minus x, I just have u. And then dx is negative 2u du. Okay, make sure everybody's accounted for. Good, now from here, let's start simplifying before we anti-differentiate. So I can cancel out this u, and I can pull this negative 2 outside the integral. So we're going to have negative 2 times the integral of 1 minus u squared squared du. Okay, now I have to open up these parentheses because I can't do another substitution. There's nothing to sub it with. So I have negative 2 times the integral of 1 minus 2u squared plus u to the 4th du. And then let's distribute that negative 2 through. So I'm going to have, or no, let's leave it anti-differentiate and then I'll distribute. Let's not make life too complicated. So negative 2, antiderivative of 1 is just going to be u. Antiderivative of negative 2u squared, that'll be negative 2/3 u cubed plus 1/5 u to the 5th plus c. Okay, now let's distribute that negative 2. So I'll have negative 2u plus 4/3 u cubed minus 2/5 u to the 5th plus c. And then we got to go back and replace u with rad 1 minus x. And since I'm going to cube it and raise it to the 5th power, I'm just going to leave it to the 1/2 power. So I'll have negative 2, 1 minus x to the 1/2 plus 4/3. U cubed would be 1 minus x to the 3/2 minus 2/5 times 1 minus x to the 5/2 plus c. That one was a doozy, but you should be so proud if you could follow along and then recreate it later, okay? So give yourself a little break and then write the problem down and see if you could do it on your own. All right, good. Now, are you wondering what in the world we would do if we had limits of integration? Yes? I'm so glad you asked. So, the substitution rule for definite integrals. Same thing if g prime is continuous on the interval now, specifically defined from a to b because we have limits of integration, and f is continuous on the range of u, which is g of x, then the integral from a to b of f of g of x is equal times g prime of x dx equals the integral from g of a to g of b of f of u du. So remember, u is equal to g of x, so you could also think of this lower limit as u of a and this upper limit as u of b. Okay, so you basically just switch your limits to be in terms of u as well, and then carry on and anti-differentiate from there. And remember, when you have definite integrals, your answer is going to be a constant. You're not going to get a function of a variable. You're not going to have a plus c at the end. You should have some value, some constant. Okay, so let's look at some examples here. Integral from 0 to 1, x times e to the negative x squared dx. Is something popping out at you saying, oh, I'm a good choice for you? Well, I'm looking at that x squared and then I see an x sitting in front of my integral. So it makes sense. I should let u be, let's put the negative in there, negative x squared. You could just do x squared, but then you have a little more thinking to do. So just clean it up as much as possible. Now du is going to be negative 2x dx, right? And I'm going to draw my little kidney bean. Here's x dx, so I want to match that exactly. So negative 1/2 du is equal to x dx. Also, I need to change my limits of integration. So since u is equal to negative x squared, I'm going to change the lower limit of 0 and upper limit of 1. So u of 0 is going to be negative 0 squared, which is 0. And then u of 1 is going to be negative 1 squared, which is negative 1. So now I'm ready to rewrite my integral entirely in terms of u. So I'm going to have the integral from 0 to negative 1, e to the u, and then x dx is negative 1/2 du. So let's put the du here. Let's throw this negative 1/2 outside. Okay, can you guys handle that? Now look, one slick move we can do is flip the limits of integration, and then I can get rid of that negative, right? I recommend doing that whenever possible. It'll be easier to evaluate. So I'm going to have positive 1/2 times the integral from negative 1 to 0 of e to the u du. All right, and the antiderivative of e to the u, one of my favorites, just e to the u. We're going to evaluate from negative 1 to 0. Let's keep that 1/2 outside. Then I have e to the 0 minus e to the negative first. So this is going to be 1/2 e to the 0 is 1 minus 1 over e. So you could write this as 1/2. If you need to get a common denominator, that would be e minus 1 over e. So you could write it as e minus 1 over 2e. All right, looks nice. Let's do another one. So you don't have to worry about backsubbing to the variable because you changed your limits of integration, right? So these are different than the indefinite integrals. Okay, example 2, we have the integral from 0 to 1/2 of sine inverse of x over rad 1 minus x squared dx. Again, this is one where if you learned your derivatives, especially of your trig inverses, it should just be popping out at you, because I know the derivative of sine inverse of x is 1 over rad 1 minus x squared. If you don't know it, I can't say anything. Just start making flashcards or something. So u equals sine inverse of x. Then du is going to be 1 over rad 1 minus x squared dx, which is exactly what I have here. Oh, so beautiful. Now I just have to change the limits of integration. So u is sine inverse of x. U of 0, the lower limit, that's going to be sine inverse of 0. Well, sine inverse of 0 is 0. And then u of 1/2, that's going to be sine inverse of 1/2, which is pi over 6. All right, yeah, you got to remember your trig too. All right, time to switch things to be in terms of u. So new lower limit, 0. New upper limit, pi over 6. Sine inverse of x, this guy here, that's my u. And then all of this dx over rad 1 minus x squared, that's just du. So sweet and simple, right? That's why u-substitution is so nice. It takes this crazy integral and just makes it a lot easier to work with and anti-differentiate. Okay, antiderivative of u is 1/2 u squared. I'm going to evaluate it from 0 to pi over 6. Leave that 1/2 outside. I'm going to have pi squared over 36 minus 0 squared. So I'm going to have pi squared over 72. Okay, how was that? Just be precise and you'll be fine. I got one more trig one for you because we just can't get enough of trig, can we? So example 3, we have the integral from 1/6 to 1/2 of cosecant pi t times cotangent pi t dt. Now look at this. If the pi's weren't there, if it was just cosecant t, cotangent t, would you know the antiderivative? I hope so. It's just negative cosecant t. So whenever you have that extra constant, for now, let's do a u substitution. Later on, you won't even need to. You're going to become so professional. So if you don't want that pi there, right, I'm going to let u equal pi t. Then du is going to be pi dt. All I have is a dt here. So that means 1 over pi du is equal to dt. Now I got to switch my limits, okay? So u is equal to pi times t, so u of 1/6 is going to be pi over 6. And then u of 1/2 is going to be pi over 2. So what's my new integral become? Well, I've got lower limit is pi over 6. Upper limit is pi over 2. Now I'm going to have cosecant u, cotangent u. And then remember, dt is 1 over pi du. So let us put the du here and the 1 over pi outside so it doesn't bother us. Okay? Now antiderivative of cosecant u, cotangent u, that's negative cosecant u. So let's bring that negative outside, 1 over pi cosecant u, and then we're going to evaluate that from pi over 6 to pi over 2. So I have negative 1 over pi times, now cosecant of pi over 2, it's the reciprocal of sine of pi over 2, which is going to be 1, minus, and then cosecant of pi over 6 is the reciprocal of sine of pi over 6, so reciprocal of 1/2 is 2. So, just a marker, please. So 1 minus 2, that's negative 1, times negative 1 over pi gives us a positive 1 over pi. All right. Good. Now, even with this fancy u-substitution that we've learned, you're going to still encounter some antiderivatives that you can't compute or will be too difficult to compute. And when that happens, what we're going to do is use symmetry to help us. Now, remember, a function is even by definition if f of negative x is equal to f of x. And if your limits of integration are on the interval from a to negative a, so evenly split about the center. Remember, an even function is symmetric about the y-axis. So you can make life easier and just double the value of your integral and start at 0. And we love plugging in 0 for limits instead of negative a. It's going to make the computation a lot easier. Let me show you what I mean. So you have some function, say it's even. So that means it's symmetric about the y-axis, right? Think of x squared. That's your most classic example of an even function. Okay, let's draw something. Hold on, let me put a and negative a. Here's negative a, here's a. I'm going to make a little function here. It's symmetric, okay? So I'm going to do my best to make a perfect mirror image on this side. And say you want the area underneath the curve from negative a to a, right? Well, you could do this whole integral here, or you could simply compute the integral from 0 to a and double it. You see how it's the same thing? So that's what this is basically saying. You can replace your lower limit with a 0 and then just double it. Leave the upper limit as is. Now, if your function is odd, by definition, f of negative x is equal to negative f of x. That means it has origin symmetry, right? Origin symmetry. This one was y-axis symmetry. And if your interval is from negative a to a, so evenly spaced about the y-axis on both sides, then the value of that definite integral is going to be 0 because all of the positive area will cancel with the negative area. Let's draw a picture to see an example. So this was for an even one. Now let's do one that's odd. So odd functions, maybe you think of x cubed or you think of sine x, something like that. Let me draw something a little fun, something with origin symmetry. I don't think that's right. I shouldn't try to be so fancy. Okay, so here's a, here's negative a. Now look at this. So the area underneath the curve from negative a to a will have exactly the same amount of positive area and negative area. So it all cancels out. So you don't even have to do anything. If you can identify that this function is odd and these limits are the same, that's the thing. A and negative a have to be the limits, like 2 and negative 2. You can't have from like negative 5 to 2. That's no good to you. But then you can just say it's 0, okay? So let's look at this next example here. We have the integral from negative pi over 2 to pi over 2. So that's your clue. Ooh, maybe I need to start thinking about symmetry, okay, and not actually try to integrate this thing. Of x squared times sine x over 1 plus x to the 6th dx. And let me tell you, even though we can use sub, it's going to be way too crazy. So let's think, maybe this is even or odd or something like that. Let's test it. So I'm asking myself, is this even, odd, or neither? If it's neither, then I have to figure out something. I can't use symmetry to my advantage. So how do I check? You evaluate f of negative x. You do one test when you're testing if it's even or odd. If you get back the same thing, it's even. If you get back the opposite of the original, it's odd. So substituting negative x for x, I'm going to have negative x squared times sine of negative x over 1 plus negative x to the 6th. Okay, in the numerator, I'm going to have positive x squared. Sine is an odd function, yes? So I have negative sine x. The only even trig function is cosine of x and secant of x. Okay, over, that's so crooked, over 1 plus positive x to the 6th. Now that negative, I can pull that outside, so I could rewrite this as negative x squared sine x over 1 plus x to the 6th. And what do you notice? This is the opposite of my original function, which means by definition it's odd. So what is the value of this integral? The integral from negative pi over 2 to pi over 2 of x squared sine x over 1 plus x to the 6th dx is 0. By symmetry, or because the function's odd, give some sort of justification. All right? So that concludes the lesson. Be sure to subscribe and comment down below what other questions or videos you would like to see in the future.